In this video, we're going to work through this worksheet on trapezoidal rule and Riemann sums. Some of the tables here we're going to have to be a little creative with, so they didn't come through all that great, but we'll see if we can make this work. So here we have a table of values, and we are going to assume that f is continuous, and we want to approximate the integral from 2 to 4 of f of x using the trapezoidal rule. So these we can see, the first thing we have to check and see, do we have uniform width trapezoids? And you can see all of these delta x's are going to be 0.5, so it is a uniform width trapezoidal rule. So that means that we can use our formula. So we're going to do our b minus a over 2n, and we're going to do that f of x sub 0 plus 2f of x sub 1, and we're going to go all those 2's, and then finally end up with 1 of the last one. So our b minus a is going to be our 4 minus the 2, and we have 1, 2, so we have 1, 2, 3, 4 trapezoids. So 2n is going to be 8. We're going to have f of x sub 0. That's going to be that first y value, 3.12. We're going to get 2 times the 3.37. We'll get 2 times the 4.12, 2 times the 3.95, and then 1 of our last one, the 3.83. So this is going to be b minus a is 4 minus 2 is 2 over 8 is going to make that be 2/8 or 1/4. We can enter that into our calculator, and hopefully we're going to get 7.4575, or you can call that, I didn't write that right, hold on, 7.4575, or you can round that to 7.458. Okay, using right-hand rectangles, now we're going to use the right side. So our first rectangle is going to have a base times height. Base is going to be our delta x, so that's going to be the 2.5 minus 2 times the height is going to be the right side, is the 3.37. And likewise, the next one is going to be 3 minus the 2.5. So these are all going to be 0.5 for the bases, and we'll have that times 4.12. So then we'll get a 0.5 times a 3.95, and we'll get a 0.5 times 3.83. So all this can go into our calculator, and we should be getting 7.635. Left-hand rectangles will look very similar. So again, we're going to take the 2.5 minus 2. This time the height will be the left side, so that'll be a 3.12. And then the next one, again, we're going to get a 0.5 for the base, and using the left side of that rectangle is going to be a 3.37. Then we'll get a 0.5 times the 4.12, and the 0.5 times the 3.95, and we aren't going to use the last one because we're doing a left Riemann sum, and that I believe is 7.28. Okay, I'm going to scroll up here a little bit. So to monitor the thermal pollution of a river, a biologist takes hourly temperature readings in degrees Fahrenheit from 9 a.m. to 5 p.m. The results are in the following table. Now we have to be careful on a couple of fronts here. Notice that we do not have uniform width subintervals there, because from 9 to 11 is going to be 2, from 11 to 12 is 1, then 12 to 3 is 3, and so on. Now we also have an issue because these aren't going in the same order. I mean, because of the clock, we don't want to say that, we're going to go 9, 11, 12, and so on. So if you want we can think of this, I think we'll be okay. Just remember we have a delta x, because I don't think we're going to cross over our, when we go to do the delta x here, we're not going to take 3 minus 12. We're going to think of that as being 3, because we're talking time here. Okay, so let's see if we can approximate the average temperature between 9 and 5. So average is going to be our 1 over b minus a, integral from a to b of our temperature function. So we're going to approximate the integral using our trapezoidal rule. So we're going to have a 1 over b minus a. I'm going to think of this for a moment as being times 0, and then this will be times 2, this will be times 3, that will be times 6, times 7, and times 8. So we can think of that as being 1 over 8 minus 0, integral from 0 to 8 of our temperature function. So we're going to get a 1 over 8 from our average value, and then we can't use our formula, so we're going to have to do individual trapezoids here. So we're going to get a 1/2 times the sum of the bases, and the sum of the bases are going to be those temperature values. So that's going to be 75.3 plus 83.1, then times the height, which is going to be our delta x, which is going to be a 2 minus 0. So there's our first trapezoid. Our second trapezoid is going to be 1/2, and the sum of the bases there, those are going to be our next two bases. So we recycle the 83.1, because we're going to use it in both our trapezoids. Then 84.8, and this time our delta time, 3 minus 2, is going to be 1. Our next trapezoid will be 1/2, and now we're going to add these bases. So that's going to be 84.8, which we've seen once before, plus the 81.1, and this time our delta t is going to be a difference of 3 hours, so we're going to put that down as a 3. And the next trapezoid, we're going to use the 81.1 again, plus we're going to get this time 78.6, and our delta t here, 7 minus 6, is 1. And our final trapezoid is 1/2. We're going to use a 78.6 again, plus the 75.1, our last one, and our delta t is also a 1. So those are the numbers. We can put all of those into our calculator, and I believe that's going to be 80.9875. 80.9875. Okay, and you can round that to 3 decimal places. Okay, I'm going to scroll up a bit. Now here's where it gets a little goofy. I don't know why I copied this way, but let's read through it first. A water tank at a wilderness outpost holds 1,200 gallons of water at time 0. And so our G of 0, I believe, well, let's see. Let's read on. During the time interval from 0 to 18 hours, water is added to the tank by a natural underground water source, a spring. During the time interval, water is removed from the tank as needed by those living at the outpost. The table shown below gives the amount of water in the tank as recorded at 5 random times. So we can see now this table here was supposed to have been up here, so you're going to have to try to kind of read through it there. So at G of 0, there's 1,200 gallons in the tank at 6.5 hours. There was 525 gallons at 10 hours, 1,209, 13 hours, 1,697, and at 18 hours, 1,310 hours. So 1,310 gallons. So down here it says, down here it says we want to represent, oh wait, let me scroll down a little bit. Here's part A. So write an integral expression in terms of G of t for the average gallons of water in the tank over the time from 0 to 18. So G of t here is the number of gallons in the tank. So the average number of gallons is asking for the average of g of t. So that's going to be 1 over b minus a integral from a to b of g of t. And in our case, since the a and b are 0 and 18, we'll get 1 over 18 times the integral from 0 to 18 of g of t dt. So that is our answer to part A. Now part B says estimate the average gallons of water in the tank over the time interval using a trapezoidal sum with the 4 sub-intervals indicated in the chart, and indicate our units of measure. Now, when we look at our chart, you're going to have to kind of squint a little bit there. So we're going to try to approximate this, and instead of evaluating the integral, we're going to use a trapezoidal rule. But you can see that our delta t's here, there's 0 to 6.5, there's 6.5 to 10, 10 to 13. These are not uniform width, so we're not going to be able to use our formula. So instead, we're going to say here's our 1/18th because it's an average value of the function. So we're doing our average value formula that we wrote down in part A. And then the first trapezoid, we're going to have 1/2, and the sum of the bases are going to be our 1200 plus our 525, and the delta t is going to be our 6.5 minus 0, which is 6.5. The second trapezoid is going to be 1/2, and its bases are going to be 525 plus the 1209, and its delta t is going to be 10 minus 6.5, which is going to be a 3.5. And our third trapezoid is going to be 1/2. It's going to be the 1209 plus the 1697. And then our delta t is going to be 13 minus 10, which is 3. And our final trapezoid is going to be 1/2, the 1697 plus 1310, and 18 minus 13 is 5. So we will then enter that stuff into our calculator, and I believe that is going to be 1139.847, and we're asked to give units. So our integral here, we had G was in gallons, and the 1 over 18, but this is gallons times hours, and the 1 over 18 is going to have a unit in the denominator of hours, and so what we're going to get is the average number of gallons that are in the tank. So our tank at any moment in time had G of T gallons, and the average number of gallons in the tank is 1139.847. Part B says, oh, we did that. So then now here you're going to have to concentrate too, because again the sketch didn't come out great. Here is our graph of f of t. You can see that there. We're going to use the concept of accumulated area to draw the sketch of the following. So first g of x. So if we're going to graph g of x here, then let's see, we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now at 0, we know when x is 0, g of 0 is the integral from 0 to 0 of anything is 0. So we know that that's going to be a point on our curve. When we look at, say, g of, let's look at the end of this part right here. So at 2, g of 2 is going to be that integral from 0 to 2 of f. And we can see that the area that we have accumulated between 0 and 2 is going to be 1/2 base times height. 2 times 2 is 4. Half of that is going to be 2. But because we're going to the left, that's going to be a negative 2. So at 2, let me put some tick marks on the y. 1, 2, 3, 4, 5, 6 for now. So at 2, we're going to be at negative 2 for the y. Then we're going to look at if we go to, say, g of 3. So g of 3, we're going to get that negative 2 that we got. And then we have another, that's going to be a 2 by 1. So that part there is going to be another 2. So together, that's going to be the negative 2 plus another negative 2 is a negative 4. So at 3, we're going to be at negative 4. At, let's see, at 6, let's go to g of 6. So now we're going to add in this triangle here. That's another 1/2 base times height, which is again 2 by 2. So we're going to get another negative 2 added on there. And so that's going to make g of 6 a negative 6. So let's see, we have right to where we wanted it. So there's our g of negative 6. Now let's go the other direction for a bit here. Let's see what we're going to get when we go from 0 to negative 2. Again, 1/2 base times height. That's going to be 2, but because when we evaluate g of negative 2, our integral is going to be from 0 to negative 2. We're going big to small, so that's going to make that be a negative 2 as well. So we're going to get a little symmetry going on there. Now, and we get g of negative 4, similar argument, we're going to add another negative 2 in there. That's going to be a negative 4. And when we find g of negative 6, we're going to add in, that's a 2 by 4, so 2 by 2 rather, so we're going to add another negative 4 to that. That's going to be a negative 8. So I guess I need a couple more tick marks there. And by the time we get to negative 4, we're going to be down here. Now, for this part in here, that's a straight line. So when we integrate that, we're going to get a parabola, something with an x squared. So as we connect these 3 points, we're going to do that with a parabola. Now, the horizontal line piece, the integral of a constant is linear. So that part is going to be a straight line. I'll try to make that look like a straight line, but you might have to use your imagination. Now, the integral of this line is going to be a parabola, and that's going to open up because that has positive slope. So I'm going to try to make that look like it's part of a parabola that opens up. Similarly, over here, we're going to get a straight line for this segment right there, which I have a hard time drawing straight lines. And that's going to actually continue all the way through. So that straight line is going to go all the way through to the end. Okay? All right. Let's see if we can do that now for the next one. So now h is going to be essentially the same, but we're going to start it at 2. So let's see, we're going to go 1, 2, 3, 4, 1, 2, 3, 4. So again, what we're going to do here is say what is, well, this time we can say g of 2 is going to be the integral from 2 to 2 of f. That's going to be 0. So we're going to be right here. G of 0 is going to be the integral from 2 to 0 of f. And 2 to 0 is again this area here, which is a negative 2, it looks like, because it's below the x-axis. But because we're going from right to left, that's going to turn that into a positive. So we're going to be up here at positive 2. And when we get g of 3, we're going to again add on, since the integral from 2 to 3 is going to be that negative 2 added on to the 0 is going to make that be a negative 2. So we're going to be at -2. And when we get to g of, what was the end of that? 4? 1, 2, 3, 4. I guess it's g of 5. Is that right? 1, 2, 3, 4, 5. I think I called that 6. That should have been back here. That should have been a 5, I believe. 1, 2, 3, yeah. Okay. So now that g of 5 is going to add another -2 to that, so that's going to be a -4. Okay, and going the other direction, we're going to see that I'm going to come up here, g of -2. We're going to go from 2 to -2. So as we come this way, it's going to treat this as a +2, but then that's going to be a -2 because we're going right to left. So that's also going to be 0. G of negative, I guess we can go all the way to, what is it, 1, 2, 3, 4, 5. So G of -5 is going to be, let's see, we were at 0 to here. We're going right to left. So we're going to go 1, 2, 3, 4, 5, 6. That's going to be, I think, a -6. So I'm going to go down a couple more tick marks and call that, I guess I got to go another tick mark to the left. It's going to be g of -5 is going to be down here. So as we said before, this is going to be a parabola. This is going to be a straight line segment, and that's going to be part of a parabola that opens up. Trying to make that look a little more bendy. This is all going to be a straight line through there. So it's the exact same shape as our red one, but it's been translated up 1. That's what we want to be able to see. And let's do one more. Now we're going to go from -4. So here we're going to go 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3. Let's see. So I'll do this one in green. So we're going to go the integral from -4 to, say, 0 of f. So as we go 1, 2, 3, 4, as we go from -4 to 0, we're going to accumulate that 2, 4, 6 that's below the x-axis. I'm sorry, we're going from -4. Let me back up. Let's go, well, let's do this. Let's maybe, I'm going to do the -4 to -4 first, so we get kind of an anchor there, because we know that's going to be 0. So at -4, we're going to be 0. Now, here's our -4, right? 1, 2, 3, 4. So if we go to the left, that integral from -4 to -5, we're going to accumulate this area that's above the x-axis, but because we're going from right to left, that's going to be a -2. When we go to g of, let's go all the way to g of -2. So when we go g of -2, we're going to go from -4 to -2. And so we're going to accumulate 1, 2, 3, 4. We're going right to left, so that's going to be a +2, +4. 1, 2, 3, 4. So that's going to be up here at 4. Then if we do g of 0, we're going to continue and accumulate 2 more of those. So now we're going to be up to 6. So that's going to be all the way up here. And then when we go to g of +2, now we're going to add that -2 to what we just had. That's going to take us back down to 4. And then going to the right, we're going to then pick up another -2. That's going to take us down to +2. Is that right? 1, 2, 3. 1, 2, 3. I keep forgetting to go all the way out to 5. Let me add one more tick mark there. And then we'll pick up another -2, and that's going to take us back to 0. So we again have our parabola that opens down. We're going to have our straight line segment, and we're going to Didn't do that scaling very good. Let me see if I can make that be a little bit better. I'm going to redraw that so it doesn't look too crazy. So 1, 2, 3, 4, 5. That's where we are. So that's going to be a parabola. And then this is supposed to be a straight line all the way through. Okay, so they're all translations of each other. So the next question, part D, when does g of x reach its maximum? Well, it's going to reach its maximum at x equals 0, and that maximum value, g of 0, is going to be 0. Now, the justification, so since this is talking about an absolute maximum, we kind of want to think in terms of the candidate test for our justification. So the candidate test means we want to know where is g prime of x 0. So those are going to be our critical points. And if you look, since g is defined as a function, g prime of x is equal to f of x. And f of x is the graph that we see here, and it's 0 when it crosses the x-axis at x equals 0. So our critical points are going to be x equals 0. And then we want to know also evaluate this not only at the critical point, but at the endpoints, which I think were g of -5 and g of positive 4. Is that right? 1, 2, 3, 4. No, g of positive 5. So we are looking for here the maximum value, and we said that g of 0 was 0, and g of -5, I think we said was -8, and g of -5, what did we say that was? G of -5 was our 1, 2, 3, 4, 5, 6, 7. Yeah, that was -8, and g of positive 5 was a -6. So that's going to be our justification, is our candidate test for why g of 0 equals 0. G of 0 is the maximum value. And similarly, h is going to have its maximum. When does it reach its maximum? Well, h will also reach its maximum at x equals 0. And our justification there would again be that h prime of x is f of x, and that's equal to 0 at x equals 0. And so we will evaluate at 0 and at -5 and at positive 5, looking for the largest value. And if we can see, h of 0 was 2, and h of 5, 1, 2, 3, 4, 5, I think was that. Did I say what that was? I think I called them g's, but I think these were actually h's. So h of 5, I think, was -4. And I think h of -5 was 1, 2, 3, 4, was -6. So we can see this is our justification for having the maximum at 2, and that maximum is, our maximum is 2. It happens at 0. Okay. So we can then scroll down here. When is the graph of k of x concave down? And k of x was the one that we did in green here. So k of x will be concave down. So k of x will be concave down when k double prime of x is negative, and that will be when, when k prime of x is decreasing. So k prime of x is f of x. So we want to know where, the question becomes, where is f decreasing? So if we come back and look at our graph of f, that's over here. Here's our graph of f, and we can see that it's decreasing on this interval from -2 to 2. So if I can scroll back, it will be decreasing from -2 to 2. Our justification is because k prime of x, which equals f of x, is decreasing on that interval. Okay? All right. Now we've got a new function here. So our function q of x is the integral from -2 of f of x, and we can see f of x shown here to the right. So our first question is, which is greater, q of -1 or q of 2? Well, q of -1 is going to be that integral from -2 to -1 of f. So I'm going to draw it in red. That's going to be visually, we're going to get that area that we have accumulated there. So that's going to be a positive number, but it's going to be a little less than 2. Now q of 2, so q of 2 is going to be that integral from -2 to 2 of f. And so we can see that that's going to be, we're going to accumulate then all of this additional area, but we're going to get a little bit of this negative as well. And so we can see, we can argue this. One way of arguing it kind of maybe smoothly is to say that q of 2 will be q of -1 plus the integral from -1 to 2 of f of t dt. And we can argue that this integral, which is the green area that we have shown, -1 to 2 of f of t dt, is clearly bigger than 0. It's going to be positive. So that's kind of a nice way of arguing that. Now, q prime of t, so q prime of x is going to be f of x. So that's the actual curve that we're looking at. So q prime of -1 is f of -1. And here's -1. If we come up to the curve, we can see that that's going to be about approximately 2. So that's going to be about +2. Q prime of 2 will be f of 2. And f of 2, we can see, is going to be negative for sure. That's going to be about -1. So that is going to make q prime of -1 the bigger one. And I don't think I said, but this is the one that was bigger on the first one. Okay. And on the next one, we want now q double prime. So q double prime of x is going to be f prime of x. So q double prime of -1 is going to be the slope of the curve that we can see, that graph that we can see at -1. And at -1, that's pretty close to horizontal. So I'm going to say about 0, and q double prime of 2 is going to be the slope of the tangent line here, which also is going to be about 0. So I would say that neither is greater. I would say they're going to be about the same. So I would say f double prime of -1 is, q double prime of -1 is equal to q double prime of 2, and this is our explanation, is that q double prime is equal to f prime. Okay, very good.